My name's Justin Ging. I'm Chief Product Officer at Acomputing. Looking forward to introducing our company today. So our mission is to deliver scalable quantum computers. We are hardware focused, building gate-based quantum computing hardware. And we will be launching a quantum compute as a service model next year as we go commercial. We have a prototype system now that we're working with partners and some early customers on, and we'll move towards the full commercial system in the coming year. So our technology, like other neutral atom companies, uses optical tweezers, so finely focused lasers that actually hold individual atoms in place so that other lasers can operate on them and control their quantum information. Different from other neutral atom companies, we use the nuclear spin of the atom as our qubit rather than the electron spin. So we use alkaline earth metals as our material, and they have a unique property of having a complete electron shell or a closed shell, which provides protection to the nuclear spin from environmental perturbation like stray magnetic fields or things like that. And this results in long coherence times. Long coherence times can be quite useful. So we recently published a paper about our record-breaking 40-second coherence time, and this is not a limit. We can continue to work on this and increase it. Coherence time becomes really important when it's paired with some things like mid-circuit measurement, where you can take some measurements, go and compute what you want to do next, and then come back and continue your operation. So super critical for quantum error correction, as well as certain hybrid algorithms. So our view of the quantum industry is that there was a time when people doubted whether quantum computing hardware could exist. And thanks to some other players, that has been proven. Yes, they can exist. And then it was, well, can they have the fidelity that we need to get to? And other players have come along and said, yeah, here's really high fidelity. But the question that we see now is, can systems scale? And that is where our technology will shine. So we have the ability to scale up quickly, apply this towards physical qubits, towards logical qubits, and then start to explore these applications that everyone talks about. So how do we scale? So we create more traps for our lasers. So we have more lasers that we put into a 2D grid now. And so our prototype system that's 100 qubits is a 10 by 10 array. Over time, we'll move to larger two-dimensional array, and then move to 3D after that. And if you imagine 100 by 100 by 100 array, that's 1 million qubits. And our atoms are spaced at 4 microns apart. So what that results in is 1 million qubits in less than 1/10 of a cubic millimeter of space. And this is all within one system. Now there's a room size supporting system with all the lasers and control electronics and things like that go into supporting where the qubits are operated on. But as we scale from 100 to 1 million qubits, we'll still be within that same size, and the room size system will be about the same size room size system. So this is why the scalability of our technology is really exciting. So here's a photo of our 100 qubit system. It is a little bit like a science experiment looking device. As we move to a commercial system, a lot of these things get buttoned up, modularized, really controlled optics. We know exactly what we want to have, and we can make this in a very clean way. So you'll see a change in the view over time. And if we wanted to peek inside and see where the action takes place, deep inside that computer is an area where we have a glass cell where we're holding our atoms and doing the operations on them in that blue area. So neutral atoms has not been talked about too much in the quantum scene until recently. And so people think, oh, this is a new technology. But actually, it is based on a lot of work that it was done much earlier. So optical tweezer work and laser cooling, which are essential to executing. These are technologies that were done as far back as the 70s and 80s and earned Nobel Prizes. And some of the theoretical work around neutral atoms was actually done in 1999 and 2000, where the hardware and the systems to control them weren't quite ready, but the idea was there. And so After a few decades of continued work and technology advancements, neutral atoms are ready for implementation now. So what's next for us? As I mentioned, we're developing our commercial system, and we'll launch that cloud service. But in the meantime, we're working with partners and customers. And so interested folks who want to collaborate should reach out. Please do. And here's some information to contact me. Thanks.